All right, welcome back to O1X graduates. We are starting now a new chapter in our learning about structural mechanics, and we're going to build on what we learned in 201X to continue our journey. So welcome to 202X Part 1. We're going to work together this summer on a bunch of things. We're going to discuss what we're going to work on right away. And just as a little preview, this, as I say, is part 1 of 202X. We're going to do part 2 next summer. So 201 graduates, you should know more or less what 201 was all about. We worked on linear elastic structures. We worked on bars in axial loading, shafts in torsions, and beams in bending. And we worked on all these structures or structural elements in the realm of linear elastic constitutive response. So typically our problems were an individual bar, an individual shaft, an individual beam, and we learned how to predict the internal fields in the structure, stresses and strain. We learned how to predict the deformation on the structure based on the loading, and we did all this for, just the elements, bars, shafts, and beams. What we want to do now is start building up our structural complexity by considering assemblages of these kind of structural elements. So in 202X, we will consider structures in which we will have one or more of these components. So for instance, we can have, say, a beam fixed to a wall and loaded, say, by a certain force. But this beam may also be supported by a bar attached to the wall through a hinge. So you may have a structure in which you have a component of the structure, this bar over here, which is under axial loading, and another part of the structure that is going to behave as a beam in bending. And we may have structures in which we have, say, multiple shafts connected by gears. So that's one part of what we are trying to do, kind of build up our structural complexity based on our elements. And the other things that we're going to do is we're going to go a little further beyond the linear elastic response. So we're going to look at things that make the behavior of the structure a little more complex. One thing that we're going to look at is what are the consequences, say, of geometrical misfits in the assembly. Say that when I assemble this structure here, I fabricated this bar a little too short. So when I put it together, it starts over already. You can imagine if I make it too short, this starts over already in tension because I have to stretch it a little bit to make it fit. So we're going to look at consequences of geometric misfit. And we're going to look at consequences of thermal expansion. So we're going to look at effects of thermal expansion. And we're also going to go further from linear elastic constitutive response. So in particular, we're going to look at elastic plastic behavior. Elastic plastic behavior. So elastic plastic behavior has to do with material response in which once you deform a structure, you have a permanent residual deformation on the structure. The permanent residual deformation is called plastic deformation. And so we're going to do this, so elastic plastic response, and in particular we're going to look at permanent deformations. Permanent deformation. And we're going to look at behavior which are time dependent. So in particular for time dependent behavior, we're going to look at simple linear viscoelastic response. So we're going to look at linear viscoelastic constitutive response. So we're going to build up on what we did for 201, and we're going to look at individual structural elements, and we're going to look at what are the consequences of these different constitutive responses and conditions on individual elements, and then we're going to look at assemblies of elements in more complex structures. So that's going to be our path this summer, and as always, we're going to start simple. So we're going to start looking at some of these effects simply for bars in axial loading, and then we're going to build up from there. So it's really a good idea if you do not have all the concepts for 201 fresh in your head, to do a little bit of review. So as always, we're going to try to help you out. So I'm going to make a little sub-chapters in which we're going to do review of 201X material for axial loading before we start this material here in axial loading. And then we're going to do a review for torsion when we get to torsion, review for bending. So you're not going to be on your own doing all this work. And the last thing I want to tell you is that because we're going to have all kinds of subscripts, superscript on letters to accommodate all these different behavior and so on, I'm going to do a little bit of a simplification in the notation for 202X compared to 201X, specifically in axial loading. So we're going to start in axial loading. And for axial loading, you remember that for 201, we had the following notation. We had for stress in axial loading, and this is the normal stress, we called it sigma n. So sigma n, if you remember, if you have a section of a bar in axial loading, sigma n is the normal stress or force per unit cross-sectional area. And to remember the fact that this is the stress that acts normal to the cross-section, we call it sigma n for normal. And then the other quantity that we consider for axial loading is the strain. So the strain in axial loading, the axial strain, we call it epsilon axial. And if you remember, if you have a bar, say that you have a bar, the initial length of the bar was like this, and then the bar deforms, and this is the deformed shape of the bar. You remember that if I look at a certain section x in the bar, this section displaces by a certain amount along the direction of the bar, and we call this displacement ux of x. The displacement of the section at x, we call it ux of x. This is where this section goes when the bar is deformed. And if you remember, the strain is the elongation per unit length, and you can write it in terms of the displacement field as epsilon a of x is simply the derivative or the gradient of the displacement field at x, dux dx at section x. So this is the elongation per unit length at section x. In 202, we're going to simplify a little bit the way we write things. So in 202, the normal stress in axial loading, we are simply going to call it sigma. So it's still the same guy. It's still the force per unit area normal to the cross-section acting at each section. So this would be sigma of x. And then if changes from position to position can be a function of x, y, and z. But instead of calling it sigma n, we simply call it sigma. And similarly, for the displacement field, instead of calling it ux of x, it's called ux of x because it's the displacement in direction x of the section at x. We're going to drop this subscript over here in most of our equations. So typically, we're going to call this guy the displacement field in axial loading. It's simply going to be called u. And it's going to be, again, a function of where you are along the length of the bar. So it's still going to be u of x, but without the subscript ux. And the axial strain, we're going to drop the a subscript. So this is simply going to be epsilon of x. So epsilon of x is going to be equal to du dx as section x. Just a little bit of simplification in the notation, but not the concept. So what we're going to do now is we're going to start working on these more complex structures. And in order to do that, it's really important that we keep straight in our mind the basic concepts of equilibrium, compatibility, and constitutive, and how these three components are going to help us to solve problems for structural mechanics. So we're going to do a quick introduction on that, and then we're going to look at each individual parts and start doing some problems right away so that we get on the practical aspect of things, and that's the best way to learn. Okay? So welcome back. I've been missing you, and we're going to have fun again, and 202X Part 1 begins.